In the last unit, we examined motion. We decided we could describe motion as constant velocity when something's speed doesn't change, or accelerated when it's speeding up or slowing down or changing directions. In this unit, we're going to look at what causes things to accelerate. Now, to understand that, we first need to realize that the difference between an object moving at a constant velocity and an object at rest is simply a matter of your frame of reference. All motion is relative. So back to the same old scenario. When you're in a bus, driving down the road, here you are sitting in your seat, you are at rest compared to everything in that bus. You are not in motion. You are in motion compared to the tree outside the bus, right? Because your position relative to that tree is changing. But if I put you in the bus and it was perfectly silent and all the windows were blacked out and you couldn't see anything outside, you wouldn't have any way to know if you were moving or not moving. But as soon as that bus sped up or slowed down or went around a curve, you would feel it. You can feel acceleration. And that's because acceleration changes motion, and a change in motion requires a force. And so a force is just a push or a pull. Force is a push or pull. That's it. It's a simple, straightforward definition. Now, we want to measure how strong forces are, and we will. You guys are familiar with measuring forces already because in the United States, we measure it in pounds. Measured in pounds in the U.S. Okay? But in the metric system, the system that we use in science, we measure it in newtons. Okay? And the reason we call it newtons is for Isaac Newton. And Newton developed his 3 laws of motion, the law of universal gravitation. He's the one that related force and motion. And what Newton was able to do, we'll talk about with all his laws of motion, but he was able to relate force to acceleration. Now, when we're talking about forces, we have to realize that the direction that you push or pull something matters. So just like velocity and acceleration and displacement and position can all be negative or positive because they're all what we call vectors. A vector is a measurement that has both an amount, a magnitude, and a direction. Force also has a magnitude and a direction. It is a vector quantity. So it matters which way the force acts. So force is a push or pull, and the direction of the force or minus sign. Just like we have positive and negative velocity and we have positive and negative displacement, we will have positive and negative force. And to help us keep track of all the forces that are acting on an object, we use force diagrams. So if you are sitting here on that bench, and I'm going to draw this bigger, and I like to draw all objects as blocks. So here's the bench, and here's you sitting on the bench. What forces would be acting on you? Well, because we are on Earth, Earth always exerts a force on you towards the center of Earth, and that force is called gravity. So I draw that arrow starting on the object on which it acts and pointing in the direction of the force. So that's something you should always keep in mind when we're drawing what are called force diagrams or free body diagrams. Forces start on the object. Now, the other thing is I'm going to label this. I'm going to label this F for force, and then with a subscripted G, or F sub G, for what's causing it. So forces start on the object and are labeled by what causes them. Okay? But of course, that's not the only force that is acting on you when you're resting on your bench. There is another force that acts on you. The bench itself does, because you are being pulled down into the bench is pushing up on you, and it keeps you from falling through the bench. So there's another force that acts this way, and that's the force of the bench. Now, you'll notice I drew those two arrows about the same length, and that's because they are the same size. Neither one of those forces wins. You don't get sucked through the bench, you don't get forced up off the bench, you just hang out on the bench. So the length of the arrow, is related to the size of force. Now, you don't have to be perfect with this, but if it's a bigger force, you should draw the arrow longer. And of course, I didn't write it, but the arrow points in the direction of the force. Now, we should take a look at this picture. Because I have forces that are acting in opposite directions, I can assign positive and negative. Usually we think of as positive is up and negative is down. And so I would say that the force of the bench minus, well, I'm going to add it, plus the force of gravity is equal to 0. Okay, and I say it's equal to 0 because neither one of those forces wins. And this is what we would call a balanced force situation. Neither force is bigger, and so they add up to 0. And really, I could subtract Fg from both sides, and I would get that the force of the bench is equal to the negative of, or the opposite of, the force of gravity. That's a balanced force situation. Those two forces add up to 0. Now, if the bus were to suddenly slam on the brakes, there would be another force on you. Okay, and so there would be a force backwards exerted by the seat's friction, and it would act this way. And so the force of, I'm going to call that the friction of the seat. If that force were to act on you, we'd have to use a different frame of reference than up and down. We'd have to use left and right. That force would be unbalanced because there's nothing pulling against it. And we can even have forces that pull against each other but are still unbalanced. Like if we had a box resting on the ground and somebody was pulling on it this way with, say, 15 newtons of force, and somebody pulled back on it that way with, say, 10 newtons of force, then what we call the net force, the total force, would be 15 plus a negative 10, negative because I chose positive to be that way, and negative would be the opposite of that. 15 plus negative 10 is 5 newtons of force. And so what we call the net force, or the sum of the forces, that's the summation sign, is equal to 5 newtons. You could also call that net force.